Grounding electrodes are essential components in electrical systems, providing a low-resistance path for fault currents to return to the source and ensuring the safety of personnel and equipment. Among the various types of grounding electrodes, the 4-inch screw pipe, 500 mcm copper conductor, and ground rods are commonly used in different applications. Let's delve into each of these components and their specific characteristics. The 4-inch screw pipe is primarily employed as a grounding electrode in deep soil conditions. These pipes are typically constructed from galvanized steel, which offers excellent corrosion resistance and ensures long-term reliability in underground environments. A pointed tip is incorporated into the design to facilitate easy insertion into the ground. The length of the screw pipe can vary depending on the specific soil conditions and the required depth to achieve an effective ground connection. The installation process involves screwing the pipe into the ground until the desired depth is reached, ensuring that it is in direct contact with the surrounding soil. The screw pipe's large diameter and threaded design provide a substantial surface area for grounding, making it suitable for applications where a low resistance ground is critical. Next, we consider the 500 mcm copper conductor, which is a large diameter copper conductor widely used for grounding electrical systems. The abbreviation MCM stands for 1000 circular mils, which is a unit of measurement that defines the cross-sectional area of the conductor. A 500 mcm conductor has a cross-sectional area of 500,000 circular mils, providing a high current carrying capacity and low impedance. Typically, the 500 mcm copper conductor is employed as a grounding electrode conductor which connects the grounding electrode to the electrical system's grounding bus or neutral point. It can also be used for connecting to ground rods, forming a grounding electrode system. Copper is an excellent conductor of electricity and offers superior corrosion resistance compared to other metals, ensuring a reliable and long-lasting grounding connection. Lastly, we examine ground rods, which are metal rods driven into the ground to establish a low-resistance path for electrical current. Ground rods are typically made of copper-plated steel or solid copper, depending on the specific application and soil conditions. Copper-plated steel rods offer a balance of conductivity and mechanical strength, while solid copper rods provide superior conductivity and corrosion resistance. The lengths and diameters of ground rods vary depending on the required grounding resistance and the characteristics of the soil. Longer and thicker rods generally provide lower grounding resistance. Ground rods are commonly used for grounding electrical systems, lightning protection systems, and telecommunication installations. They are typically driven into the ground vertically, with the top of the rod exposed for connection to the grounding conductor. In some cases, multiple ground rods may be connected in parallel to further reduce the grounding resistance. The selection of appropriate grounding electrodes depends on several factors, including the soil conditions, the required grounding resistance, the size and type of electrical system, and local electrical codes and regulations. Soil conditions play a crucial role in determining the effectiveness of grounding electrodes. Soil resistivity, which is a measure of the soil's resistance to electrical current, can vary significantly depending on factors such as soil type, moisture content, and temperature. In areas with high soil resistivity, it may be necessary to use longer or more numerous grounding electrodes to achieve the desired grounding resistance. The required grounding resistance is another critical consideration. Electrical codes typically specify the maximum allowable grounding resistance for different types of electrical systems. For example, the National Electrical Code, or NEC, specifies that the grounding resistance for a single grounding electrode should not exceed 25 ohms. If the grounding resistance exceeds this value, additional grounding electrodes must be installed in parallel to reduce the overall resistance. The size and type of electrical system also influence the selection of grounding electrodes. Larger electrical systems with higher fault current levels require more robust grounding electrodes to handle the increased current flow. The type of electrical system, such as a residential, commercial, or industrial system, may also dictate specific grounding requirements. Local electrical codes and regulations must be followed when selecting and installing grounding electrodes. These codes provide detailed guidelines on the types of grounding electrodes permitted, the installation methods, and the required grounding resistance. Compliance with these codes ensures the safety and reliability of the electrical system. In addition to the selection of appropriate grounding electrodes, proper installation techniques are essential for ensuring effective grounding. Grounding electrodes should be installed in locations where they are in direct contact with the soil and are protected from physical damage. The connections between the grounding electrodes and the grounding conductor should be made using approved connectors and methods. Regular inspection and maintenance of grounding electrodes are also important to ensure their continued effectiveness. Grounding electrodes should be inspected periodically for corrosion, damage, and loose connections. Any issues identified during the inspection should be promptly addressed to maintain the integrity of the grounding system. In summary, the 4-inch screw pipe, 500 mcm copper conductor, and ground rods are essential components in electrical grounding systems. The 4-inch screw pipe is suitable for deep soil conditions, while the 500 mcm copper conductor is used as a grounding electrode conductor or for connecting to ground rods. Ground rods are commonly used for grounding electrical systems, lightning protection systems, and telecommunication installations. The selection of appropriate grounding electrodes depends on factors such as soil conditions, required grounding resistance, size and type of electrical system, and local electrical codes and regulations. Proper installation and maintenance are also crucial for ensuring effective grounding.